Oops, that's not what I was supposed to do.
Oh, whoa, whoa. Boy.
As far as what you should store, that goes to where your slices are. Your slices dx or dy. Dx, so you'll need dx stored.
Mr. Haley's not.
Mr. Haley's not coming?
Mr. Haley is not here.
Thank you. That should be satisfactory.
Wait, no. Can you move that?
What? Why don't you find them yourself, lazy? I gotta do it for you. I taught you how to fish. I don't want to give you a fish.
I just need to see
So what's the volume method for semicircles? The typical form. Pi over 8, which comes from a kind of tweaked form of 1/2 pi r squared, right? Pi over 8. Diameter squared. Then the question is, what's the diameter? Upper minus lower. So, is the upper the line or the parabola? Line. So x minus 2 minus x squared plus 5x. Again, that's not washers. It's not r squared minus r squared. It's one minus the other, the whole quantity squared. And obviously there is a difference. So, please, I beg you, please type in the pi over 8 first. It's the most common mistake that people forget the pi over 8. They think, oh, I'll put that in later. I'll do the integral. You won't. You'll forget. So put the pi over 8 over in first. Oops, darn it. Then A to B. If you've got the functions in and you remember which one is which, you can call up the functions. I don't really remember which is which. I want to do F2 minus F1. F2. Surely you need to know which one's in which place in the menu. Squared. Don't forget the square. Also a common mistake. Boom, diggity. Did you get a volume of 2.3695? Okay, here we go then. Today's lesson. Okay, the fundamental theorem of calculus is the idea that integrating a rate of change gives you an amount of change. They're huge. I mean, like this thick of books just on what does the fundamental theorem of calculus mean. You can look at it in a million different ways, but at one basic level, the fundamental theorem of calculus says if you sum lots of rates of change times amounts of change, you get net change. Now, net change then in the original function. Net change then would be what f of b is at the first or the upper endpoint minus the lower. And it could be a lot of things, but that's the fundamental theorem of calculus. Sometimes it's subtitled the existence of the definite infinite. First time that this idea was introduced in it. Okay? Now there's a second idea to the fundamental theorem that's a little like this. this, one level you could look at it as the antiderivative of the derivative is the function. Once you agree that that's kind of what it says. All right. Now say you switch that then. What about the derivative of the antiderivative? That's the function. They don't do each other. Now that's what we're going to do today. That's fundamental theorem part 2. This is fundamental theorem of calculus part 1. It's not new. You've been doing it since set 47 or so. I think it was in there somewhere. It is one of the biggest ideas of all of mathematics. Fundamental theorem part 2 is a little different. If you think of an integral as an accumulation of change, then you could also think of this problem as g is the accumulation of change, or in this case, of that change is represented by the area under f, yeah? From -3 up to some any varying left or right endpoint x. So if I wanted to visually show what does g of -2 mean, then that would represent the integral from -3 to -2 of f. And so it would mean that, yeah? All right, so far so good? And if I said that's g at -1, that's the area from -3 to -1. And so it would be this. Everything good so far? Just reviewing what we know. All right, now then. Say I talked about, today's idea is the rate of change in the area accumulation. When is G accumulating area the fastest? From -3 to -2 or from -2 to -1? When is it accumulating more area? In which of those one unit intervals is more area accumulated? From -2 to -1. Now, that's surely not by virtue of the x, because the x is the same. The reason more area is accumulated in the second region is because the function's higher, right? All right. Now, in essence then, if what we're talking about in calculus is the rate at which area is accumulated depends on how high the function is. Now, in calculus speak then, that means I want to talk about the rate of change in the area accumulation. Well, the rate of change in the area accumulation is g prime. And that's the derivative of the left side. You follow? Well, just like here, we said the antiderivative of the derivative is the function. We're kind of switching those here. In essence, we're saying the derivative of the antiderivative is, say it, the function, okay? Or f. Now that is actually exactly what we said here. The rate at which area is accumulated depends on how high the function is. Now this, I mean, it seems to make sense, and most students do fine with it. We'll start off easy and then gradually get harder. The idea, though, is that the derivative of the antiderivative is the function, pretty much. Okay. Now, what makes this a gotcha kind of question is, imagine if this endpoint, instead of just staying stationary, move. Oops, that's not what I wanted. Okay, what if this right edge moved? Then if that, whatever, if that moved, then surely the rate at which area accumulated would depend on two things, the function and how fast that line was moving. That's more of a chain rule deal. That's more in the abstract. We'll get to that in a second. But let's start off with something that's really easy. Students love these because they take zero work and most students get them right. All right? Now, I'm gonna go through this stuff a long way, just to cover my tush when you get a hard one. But for 80% of these, there's a short way that that'll always work. All right, so I just wanna make sure you know both ways. So this is what a question will look like, all right? The derivative of the area accumulation function or the antiderivative function here. Now again, think visually that this is some kind of parabola and we're accumulating area from 0 up to some right edge. And this is then asking, what's the rate at which that area is being accumulated? That's the question in plain old English, right? Now the long way would be to work inside out. The long way would be to say, all right, I got to take the antiderivative, which is 1/3 t cubed minus 3/2 t squared plus t from 0 to x. Then doing the definite integral part of that. Wouldn't that be 1/3 x cubed minus 3/2 x squared plus x minus a bunch of zeros? And then the last step is to take the derivative of that. With respect to x, the derivative of 1/3 x cubed is x squared. Derivative of negative 3/2 x squared is negative 3x, and the derivative of x is 1, and the derivative of that constant, that's nothing. Now, surely then, we get an answer that was totally logical. What do you reckon the shortcut is? Looking at that, how could we have seen that this was going to be the answer? Yeah, it basically put the x in because these two are canceling each other out in effect. The derivative of the antiderivative, right back to where you started. You with me? The only difference being that x gets substituted along the way, so your final answer is a function of x, or the upper limit, not t. X got put in along the way, right? The shortcut then is to say that the derivative of the antiderivative is just the function in the integral with x substituted in. Now, with that said then, would you use that shortcut idea for those two? If you're at all with me right now, that should take about 5 seconds each. Okay, so what's the first one? Sine of x cubed. That is true. The next one, you might give a little bit of a pause here, in that you can see the slightest difference here is that that's a 5, right? Is that a problem if it's not 0? It isn't a problem. Now here's why, on 2 levels. First of all, on the graphical level, when I talk about the area, the rate at which area is accumulated, it doesn't matter if I'm starting here or here. What matters is the right endpoint and how it's changing. It's still, when I'm still at this point in the curve, it's a non-issue. Also, if you think on the analytical level here, if I put 5 in, yes, okay, I would get a bunch of numbers here, not 0, but then I'm taking the derivative of those 5-ish numbers, and whether it's 0 or numbers, isn't the derivative still going to be 0? So this is not a problem. The derivative of a constant, whether it be 0 or some other constant, is always going to be 0. So that left edge being non-zero, not a problem. You with me? And so this was log of arctangent of x. Okay. Now then, let's go to gradual Ickies, if you will, all right? Sometimes the variable is in the lower limit position. Now, I'm going to start to introduce a modified shortcut, all right? Now, the modified shortcut goes something like this. I am going to take the derivative of the definite integral, and when we do a definite integral, we find the antiderivative at the upper minus the antiderivative at the lower. You with me? Now, rather than actually finding the antiderivative this time, I'm going to say let capital F be the antiderivative of that. Now, that's wonderful on 2 levels. First of all, it saves you from having to actually anti-differentiate it. Second, there are a lot of integrals that can't be antidifferentiated along the way, and that shouldn't get you hung up. So just let f equal the antiderivative. So wouldn't this be f at 4 minus f at x once I took the antiderivative and substituted it in the upper limit minus the lower limit? You tracking? Now then, when I take the derivative of each of these components, what is the derivative of f of 4? What is f of 4? Is it variable or constant? Constant, and therefore the derivative will be 0, okay? Minus, what is the derivative of capital F, which is the derivative of the antiderivative? It's just the function, but not with t in it anymore, with x. And so it would be something like the opposite of x squared minus 3x plus 1, or if you like, negative x squared plus 3x minus 1. So in essence then, what happens when the x is in the lower limit position? It's the negative of the function, right? So would you do those two, please? ¿Listos? Sí, estamos listos. The first one, what is it? Negative cosine of x cubed. And another? Okay. All right. Obviously, I'll pause and say there's no plus c. These are definitive, so you should never have a c anymore. Sometimes I'll see it. You down? All right. The worst case scenario on these is when you get a function within a function. Now this is pretty complicated, and you would have to really be stretching it in math modeling when you use this to get a case like this. But it sometimes is the case that it's a function depending on a function in the top edge of the integral. It depends on some other kind of relationship altogether. Look at a good one from a college textbook about this and when it's used, but I'll try and find it. I don't remember this. All right, but the point is this, right? Let's go through this slowly, and we're going to see how the chain rule's got to be used. I'm going to go the long way so that once we see what's going on, then we can use the short way, right? But wouldn't you agree that the long way is to say the derivative comes later, and I take the antiderivative at the upper minus the lower? And again, although cosine is pretty easy to integrate, I'm still going to bypass that and just let f be the antiderivative. F at x squared minus f at 2. You cool? All right, now I'm going to take the derivative of that, and you can see where I'm going to get a chain rule. Now, because I have x squared now, I have a function within a function. That's why I'm going to need the chain rule. So on the derivative of that, I'll take the derivative of capital F, which is to say the derivative of the antiderivative with the inside the same. So what is the first part? Back to the original function, but with x squared in it. But then by chain rule, then I have to take times the derivative of the inside, which is 2x. Now what about the derivative of this guy here?
0.
It's 0, it's constant, so no issue. All right, so there's our final answer. You can see then, when you have a function in one of those limit spaces, you're going to have a chain rule going on. So what about this guy here? Let's do this one together. Should we do let's try without the shortcut. What would it be? Or with the shortcut? Okay, so what would we do? Natural log of sine of x squared minus 3 times cosine of x for the chain rule for the derivative of the sine function. You follow? All right, try those three, please. And we'll move on to the second and pretty much unrelated. Okay. All right, how we doing? We good? Okay, so let's say this guy, did you get something like 1 over the square root of 2x cubed, but then by the derivative of the inside, 6x squared, right? This one, does that say e to the x?
Yes.
Okay, so arctangent of e to the x squared times e to the x. And then throwing you a curveball, what is this one? Sine of root x times the derivative of the inside there is 1, so that's cool. And that it? Plus or minus? Minus sine of root of x squared plus x times 2x plus 1. That's about as ugly as you can see. Okay? Are you with me on that? All right. Let's go on to the second idea, and that is the idea that I touched on Monday in that fun sheet, quote unquote, and that is that log is often defined as the area under the 1 over x curve or 1 over t curve. Okay? So if you were to think of log of 2 in a pre-calculus way, log of 2 in a pre-calculus way would mean e to what power is 2. That's the pre-calculus way. It's you're talking about the exponent of e required to make some kind of. In a calculus way, you'd say log of 2 could be represented as using the 1 over t curve and going from 1 up to whatever number you put in. So log of 2, if I were to graph the 1 over x curve really well and then try and use little, like graph paper squares to find the area, then log of 2 would represent that area in that shaded region. Now, that actually makes tons of sense. If you think about it, if we were to do this a long way, what is the antiderivative of 1 over t? Natural log of the absolute value of t from 1 to x. What's the log of x? Oh, sorry. What's the log of 1, rather? 0, right? So it makes sense that those two are one and the same. Now, the beauty of it, though, is that we don't find log of 2 by anti-differentiating. We find log of 2 by then using some kind of trapezoid or rectangle method then to estimate that area under the curve, right? So, for example, if I wanted to estimate the log of 4 using 3 trapezoids, then the first thing I would do is translate as an integral. By this definition here, it means that the log of 4 is the area from 1 to 4 over 1 over t dt. Right. Now, we're going to estimate the integral using trapezoids. Now, just so we're clear, the question sometimes is, why estimate it at all? Why not anti-differentiate? Well, if I anti-differentiate it, what do I get? Natural log of 4, which leads me to the conclusion that the natural log of 4 equals natural log of 4. Great work. So true. Not at all helpful. Okay? So you're trying to use some kind of other method to get some weird log of 4, what does that even mean kind of thing, and using it, translating it into something that's equivalent that is doable, right? So we're going to use 3 trapezoids. If I use 3 trapezoids on a region that's 3 wide, then I will have a delta x of 4 minus 1 divided by 3 chunks, or 1. So, remember there are 2 different types of trapezoid problems. There's equal subdivisions where you factor out the delta x and over 2, and then there's unequal subdivisions, often that come with a table, and those you have to just do trapezoid formula plus trapezoid formula plus trapezoid. Which one is this? Is this an equal subdivision factor out case? It is a factor out case. We factor out delta x, which is 1, and the half of the trapezoid formulas, that's there. All right, assuming we let f equal 1 over t, then the first value in my bracket is f at 1. And then, what's my next? Got it. Next thing I write. 2f, and why is that 2 there? Because it's used twice. One for a trapezoid on the left and one for the trapezoid on the right. That happens at the interiors, all right? And then what? 2f at 3 plus f at 4. We could do this without a calculator. Calculators are for the weak. I have a mistake in my error or my work there. What's wrong?
It's not equal.
Yeah, that's an approximation. That's bad math. We're approximating it. There is error in here because of the area of those trapezoids not being just like that curvy area, but the area is pretty small, you can see. All right, so 1/2 f at 1. Given that f is 1 over t, or whatever you put in, then f at 1 is 1 plus 2, what's f at a half? Or f at, darn it. It's a half. Good job, me. What's f at 3? A third. And what's f at 4? 1/4. Good job. Again, way to go, me. This is then 1/2 of 2 plus, what's the common denominator between thirds and fourths? 12. So 2/3 becomes 6/12? 8/12? 8/12. And 1/4 becomes 3/12. And that's a 1 out there. All right, so this is 1/2 of, what do we got there? 11/12 plus 24/12. Am I doing that right? 24/12 plus 11/12, so 35/12. That would be 35/24 is our estimate for the log of 4. You with me? Natural log. Okay, now it would be great to know if that's a pretty good estimate or not. The graph tends to tell me that's pretty doggone close. There's not a lot of error there between the trapezoid area and the curve area. But let's see, we could at least find an upper bound using the old trapezoid upper bound idea. We know that the error is less than b minus a cubed times m over 12 times n squared. If you don't have that memorized, you kind of stink. Maybe it's because you're on your phone in my class. But it also might be that you're just not very good at memorizing. So I will give you that. That's not going to be something you have to have memorized on the AP test. So don't worry. All right? Now then, the error is less than or equal to, what is b minus a? What are a and b? Okay, so they represent the area. In this case, then, 4 to 1. 4 minus, or 1 to 4 rather. All right? M, I remind you, is the max of the absolute value of the second derivative on the interval. In this case, from 1 to 4. Now, if the function is whatever's inside the integral, now it's always, it's very common that people think, oh, the function is log, because that's the whole point, I'm estimating log. No, that trapezoid idea corresponds to the area under the curve, and so the function is not log, it's 1 over t. Okay? That is the area of the function you're talking about in the integral. F, which is t to the negative 1. The first derivative is negative t to the negative 2, and the second derivative is positive 2t to the negative 3, or 2 over t cubed. Now I'm trying to find what's the greatest possible value of that function on 1 to 4. It would be, okay, so I think I understand what you're saying, but I think you're misspeaking. What's the greatest possible, at what x will this be at its greatest? 1. But what is the greatest value? 2. Okay. So the max is 2. This is at its greatest when t is at its least. T's least is 1 in this case. So the max is 2. With me on that? All right. 12, and what is the n that we used in this case? 3. We used 3 trapezoids, and it stands for the number of trapezoids. So this here tells me not the error. Please don't ever let me hear you say the error is this. I don't know the error. If I knew the error, then I'd know the exact. The error is not more than whatever this is, 3 times 3 times 3 times 2 over 12 times 3 times 3. So I got your 3s, got your 6s, 1 and 2. So I'm feeling 3 halves. So yeah, is that what you got there? That's what I said, 1 half. All right, so the error is not more than a half. Now that doesn't mean, again, the error is a half. The error is probably less than that. Definitely less than that, but yeah, that's the idea. All right, then last but not least, common question. If you wanted to estimate the log of 10 with error less than 100, how many trapezoids would you need to use? So the log of 10 represents the area under the curve from 1 to 10, and what curve are you finding the area under? 1 over t dt, all right? Now, to get that estimate from 1 to 10, so that the overage, wouldn't you agree trapezoids are going to overestimate here? So that the overage is less than 100, that would necessitate, probably a good number of trapezoids, although the curve is decreasing once. So that's the question. So what do I do? So should we start using our trapezoids, or should we go to the error bound idea? Okay, so in the error bound idea, it is sometimes the case that people put things in the wrong place. People will say 1/100 is less than or equal to. That is definitely not the case, because 1/100 is not the error. 1/100 is a bound for the error. So it's more like a 3-part inequality. Error is less than or equal to b minus a cubed times m over 12n squared, and that in turn needs to be less than 100. And I think you'll agree that if I could make this part happen, then the error would be less than 100th as well, right? So the 100th doesn't go there. If you do that, you'll get a stupid conclusion that says, in order to get my error small, it needs to be less than 4 trapezoids. That's a silly conclusion. You're not ever going to get less error by using less trapezoids. So putting that in the wrong place will make you look foolish, really. All right? So that said, let's move. The error is not to worry anymore. B minus A, in this case, is 10 minus 1 cubed. And m, looking at with our previous work here, what would m be in this case? If it's still 2 over t cubed, but now the max on 1 to 10, what's it? It's still 2, because the right edge is not to worry. It's the left edge that matters for us, all right? And then 12n squared, n is to be determined, and that needs to be less than 100. And they said less than, not equal to, so that should be a strict inequality, not equal to 100, less than 100, right? All right then. Isolating this, you want the n over here. When I multiply by a positive, do I need to switch the sign? No, so we're cool there. N squared is going to be there, and I don't have to worry about all those doggone inequality rules, which really make my life hard. Likewise, I can move 100 over there, and that's fine too, because it's positive. So I have 9 cubed, 2, and 100 in the numerator, all over 12. And n squared on the other side. Now you could pick up your calculator, probably find this quicker. I'm stubborn in that sense. So what do we got? 243 times, so 24,300. 12,150? No? That's not right? Ha! All right, so then, n is greater than, what's that, probably greater than 100 and 111? 111? Okay, so it's, say it again, the 110.227. So to answer the question then, again, guarding from looking like an idiot, you're not gonna say, I need 110.227 trapezoids, that's stupid. You would say you need 111. Parenthetically, I guess you could say or more. And then you hope they don't say, okay, now estimate it, because then you have to figure out how to program your calculator to do it, because there's no way you're doing 111 trapezoids. All right. In the interest of time, I think I'll leave the Simpsons rule out. If you're going to be a mathy person, engineering kind of person, Simpsons rule is a really awesome idea of a weighted average between rectangles and trapezoids. It gives a great, I'm talking a really right-on estimate of area under the curve when you're dealing with functions. I put it on the paper, and it's not hard for you to master once you've done trapezoids. It's fairly similar. So I'm going to let it go. All right, here's your answers to 97 extra practice. Let me know what you'd like to talk about. You need this? 97 extra practice.
Oh, I got the first one.
Okay. You got the first one wrong. That's a bad start. Okay? We'll talk about one. Or do you know what your mistake is? Let me know if you disagree. It's entirely possible. I make a mistake. One feels like it's easy. Why did you say 1 minus?
I didn't know. Was it 1 plus? Or is there no plus? Oh, there should be. I missed it.
Why is that a mistake? It feels like
When you do that, because it is a circle.
one and a half after you do this.
Yeah, no. Oh, that's what I was gonna say. Like, it's just the top half.
Yeah. Until I have the correction. That's the
It's actually not that easy.
Oh, is it? How long did it take?
No, it didn't take that long. It just, you don't really know. It is.
Yeah. It doesn't clear stuff up. I had a lot of questions yesterday. What about this? That's good stuff.
Oh, I did too.
All right. Let me know if you have questions. If it's all of it, so be it. Except for the first one. Excellent. You got the area. Is there an order in which there are some are more used? Just all of them? Okay. Just all of them. All right. Let's start with B. Are we cool?
Yeah.
All right. So B is more of the old style revolution. So you should go to the volume of revolution as shells, washers, or discs. You should draw yourself a little picture. You don't have to draw it on a slant. And if you go around y equals 1, then it would look something like this. Now let's go to choosing. What is, to the extent possible, what variable do you want to use, x or y? X. You want to use x because in using x you only need one integral, but anytime you use y you'll need two. If you use x, then don't your delta x's go this way? Yeah? And so your revolution would be something like this, yeah? So it's a washer. So we then say washers are pi big R squared minus little r squared, and we said dx, yeah? Okay. Now is the hard part. Big R is a vertical distance. It's upper minus lower. What's upper, what's lower? What's this?
1.
Upper is 1. And lower? Lower is on this curve. What's lower? That's not the root x curve. This is the root x curve. E to, oh, sorry. 1 minus e to the negative. Okay? So what's little r? Which is here. Upper minus lower. What's upper? Minus c. And why did I just do this?
No, I mean, I got the, upper limit.
Oh, you did, okay. So then your limits are from
0.238.
point 238.
Yes, I think I got like
Okay, so
that
that's
stuff
where-
right. I just think it's like the upper limit.
Okay, so you need to, yeah, actually, I mean, when I say upper minus lower, don't just say it, actually say, all right, what is this upper mark? Oh, it's 1. What is this lower mark? Oh, it's this curve. So, how about C then? E, is that a C?
Ooh, C, yeah.
C.
I didn't know what it meant by like the length.
Okay, so C,
It was like,
cross section's perpendicular, all right, so this one I can definitely give you some pointers for, so it looks like that, yeah? And they're, jump to the perpendicular or parallel, they're perpendicular to the x-axis. If this is the x-axis, then perpendicular would be at a right angle. We're talking slices this way, yeah? Okay? Now, they're rectangles with height 5 times the length of the base. So if this is the base, then the height would be 1, 2, 3, 4, 5 of those. And so it's some really crazy, tall kind of figure like that, yeah? All right. Now then, if you say the volume is, you're always on these going to say the volume is the sum of prisms. Go geometry. In this case, the area of the base is a rectangle, so it's base times height. And then I'm going to do actually one more geometry step. I think will be what the key is to getting this right. What's the relationship between B and H?
like when I cut it, or,
Read it more carefully.
is it
The height is?
height is 5 times the length.
The height is 5 times the length of the base. So if the height is 5 times the base,
So it would be five. What it was like this.
right. So what we want to do is 5 times the base squared is dx. Now the only question is, well, what's the base? Well, here's the base. It's upper minus lower. So what is upper, what's lower? You're just saying stuff. Got it? Here's, oh yeah, you're right, sorry.
Yeah.
I apologize, that was rude. You're right, square root of x, true that. And lower? From A or whatever it is, 0.238. Cool. That's where I got that. Alright. Moving on to what? C? D? I mean?
Yeah, so did you get a shell for that?
I did a shell for that, yes.
Okay, so then what would be the,
So D.
like it's just inside of the anti-gravity that gets to.
Right. So here's 5, here's a reflection. You said using X. So what are the two components to a shell? The height and the radius, right? And it's dx there. Okay? So the radius. Locate the radius. Say, is it horizontal, right minus left, or vertical, upper minus lower?
Right minus left.
It's horizontal, right minus left.
So it's 5 minus.
So this is the hard part. People say, is it 5 minus the square root curve, or 5 minus the e curve? The answer is 9. It's 5 minus x. When it's 2, when there's a slice of 2, the radius is 3. When there's a slice of 1, the radius is 4. So it's always just 5 minus x. The height is upper minus lower.
So that would be where the expectation.
That's where the
Okay.
point 238. Okay?
Okay.
Alright. E.
So that It's a semicircle.
Right.
So, not, well, like, just for the inside, would that be 1 minus?
No. So you're here, and the cross sections are parallel to I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All students like volleyball players, junior individual weekly support, and senior high will be double volleyball. Stop by Miss Lee's office, the main office, to get your entry form.
So, what's the diameter? There's the diameter. It's vertical, it's upper minus lower.
Oh, so that's minus. Oh.
Okay.
Julianne McCullough is an outstanding physical student.
That's hard.
Julianne's
Yes.
actively participates in class discussions and provides clear explanations of this difficult concept. She has positive interaction with classmates and is a great lab partner because she is fun and focused in the lab. Plus, she utilizes scientific concepts
Okay,
outside the
so the hard part by far of this is the cross sections from this way.
Plays amazing music on a string instrument. She was nominated by Kentucky.
Alright, good. Now because they go that way, then you're talking dy thick. And that is gonna suck because that's two different right minus lefts. There's some region that's right minus the square root curve, and there's some region that's right minus the e curve.
Your favorite
So
Dublin
there's two
teacher is a student in the annual improv show. The melodrama that kitchen book. Teachers performing include Miss Ford as a pussy mom and Mr. Ray, her name is his son. Show starts at 6:30 and tickets are sold
So it's not
to the
gonna
door
be
for only $5.
Yeah.
What's the basic idea on equilateral triangle?
Isn't it, number 4?
Okay? So the first region will be side squared dy, and then what is the lower set of rectangle triangles right minus left of these? Look at the right, look at the left. What's the right? What's the left? Right is always
Is that 5?
this.
Yeah.
That's 1.
That's 1. Okay, so the right is 1.
Right is always 1. In this lower region, left is the e curve, right?
And then the other one is 1 minus x.
Oops. So the problem though is I just wrote that, but it's dy.
Yeah.
So that's no good. I'm going to need to put that in y terms, right? So if y goes into the negative 3x, log of y equals negative 3x. So x is log of y over negative 3. And likewise, instead of square root of x, it should be y squared. And then the limits of integration, you need the intersection, the y of the intersection, and the low point here, and the high point here, right? The low point you can get without a calculator. It is when the e curve equals at an x of 1, right? So that's either negative 3 for the lower part. The upper part is the intersection y, which is 0.488. I found that by intersection calculator. Okay. In the upper region, it starts at 0.488 and goes up to when the square root curve is at x equal 1. So that's 1. Okay?
Can we do
Which one?
just
Sure. So here's sine y equals 2 pi x. Looks like that. Oops. It actually meets here at the peak. You with me? In B, they say it's revolved around the x-axis. So if you, oops, I didn't mean, if you revolve this around the x-axis, you could use x or y here, but if you use x, you get a wash, right? So the volume of pi, the x, what's big R? The upper is the sine curve and the lower is 0. And what's little r?
the line.
Line. So,
Okay.
okay, and they give you the intersections. And then C, if you use x there, you're going to get a shell. If you have this region, so you go around the y-axis, using x, you're going to get a cylindrical shell. Do you agree?
Yeah.
Okay, so you need to know R and H. What is R?
Is that just X or
X.
just Y?
It's
Or
X. Yeah, it's X. It's horizontal X. And what's H?
Upper minus lower.
Right. So the upper is the sine of the line.
Sine.
Sine minus 2 over pi x
Okay.
dx. Okay, that's
Thank
right.
you. Hello. How are you?
Good, how are you?
Good.
Hi, B.
Oh, we're taking a test.
Oh, that's
It's an unspoken rule that this is not my seat. This is an
all the
unspoken
more
rule.
reason you should sit where you belong. No. Sorry, baby.
I mean,
Yes, assigned seats. Less monkey business on a test day, not more. That's what the face of golf looks like. When I think golf, where do you see guys?
Wait, do we have to stand on our side face for test day?
Of course you do. That's what they coach question. Why are you asking me that?
Well, usually you make us stand on our side. Usually you let us sit where we want.
It's usually because all the guests are faced that way. But these are already mine.
Oh, can you send me?
Yeah.
Wait, you can go full third?
Austin, you have a pencil? No, thanks.
I had a pencil by off.
Surfing TA long?
It's about a normal.
Oh, yeah. This test, I try to like figure it out, but I never get it is. Okay, you haven't actually seen for like
Oh, Nathan, I got you your shot.
Oh, I know what you meant. That was the one that was good.
That's why I need you to take the test, otherwise you can't take the test. All right, would you please get out your, what else is? ID 98. I think it was not foundation.
See, I did yesterday.
First day university. So I don't have any. Anything I have somewhere? Pass them to a corner, please. Unfolded, do not fold them. It does not help me to fold them. It makes it worse. Thank you. Unfolded to a corner. Thank you. Okay. Second order of business. I want to take this quick so you have as much test time as possible. But this year, PTA, you just turned your CTA. Pythagorean theorem and such, and it jokes. Okay? For many of you, I got it, but from what? 7 people, I did not get it. Now, I actually have a pretty good sized stack of about 8 papers here with no name from your 2 classes. So it is entirely possible that if you're one of these people, you turned it in, but you didn't put your name on it. So if that's the case, after the test or some point in the period, see if one of those is yours, if you feel like you did it and you did turn it in, and see if one of those is yours.
Wait, what does that all stand for?
There's not a note quiz. Next order of business. Last order of business. Next order of business. The PTA. I am going to give you minimal instruction on my thing is this. This is pulled off a CMAS kind of preparation website. I want you to be able to do your best, and so just to kind of get you used to the format. Now, because these were pulled from an actual computer screen, there's some stuff that needed clarification. For example, Part A said use the drop-down menus to complete. Well, of course, there are no drop-down menus, so you're just going to choose or circle one from each of the drop-down menus. But if you just read carefully, it'll go a long way. Most important, I just want to get you practice on adapting what you know to a slightly different question. These aren't Saxon questions. They're more like some guy in Washington writing these questions. They're big ideas of math that you've studied. You just have to figure out, how is this like what I've done before? Is this a distance rate time problem? Oh, okay, it is. I do it this way, right? Don't ask me for help. I'm not going to clarify. I can't clarify the CMAS. You need to practice trying to work out the best you can. If you just read, it'll go a long way, right? Just read. People came up to me basically, in essence, their question to me summed up, could you please read this for me? Read yourself, okay? Part of reading, by the way, is not just think you understand, but reading goes well beyond just being able to decode the symbols on a page and to speak it. Actually understanding what they mean, that's reading. Right? Boom, clear your desk, please, except for a pencil, and let's test. Testing time will save you. You may not have more tests if you don't get done in the period, and I guess that's what you get. If you're a slow worker, please don't get hung up on any one question.